Hello, Michael.
Hello.
Hello there, Michael.
Hi, Brendan. How are you?
Yeah, okay.
Awesome. As the time changes, creating any difficulty over there in London?
Yeah, well, I mean, it would have been 8 o'clock would have been now. Now it's 9 o'clock.
You're going to get to go to bed early tonight then, huh?
Yeah, that's right.
All right. How's everything else going?
Yeah, it's going okay. I didn't get down to much programming. The ETT stepper is a when I look at it, it's a little bit beyond me, beyond my level of programming. But I'm going to try and understand it as much as I can, you know. But
Yeah, that's what I remember also when I was going through it is it does take quite a bit of programming background. Yeah, and I was starting to dig into it myself, but I was just too busy doing other things. Yeah, but it's a good program. What's a now? I remember I was talking with Matt back in the day a few years ago, and he said that he just used Mathematica at first because it was simplest.
yeah,
And the only reason he actually went to ETD Stepper was because uh, he needed some more flexibility with the algorithms.
okay.
You know,
I noticed the
I guess.
Mathematica one is quite small. It's not that big. It's kind of like 100 lines or something.
Oh yeah, I see. I don't have that. Yeah, yeah, I haven't seen that.
Justin was
So
on. I came on at 8:30, and Justin was there. And then we signed off because he was going to come back at 9.
well, that's now, right?
Yeah, it's now. So it's now in London. It's 7 minutes past 9.
Mm-hmm. I remember Dr. Paul. He had missed one of the meetings, and I think it was because he was sleeping or something. And if
Okay, all
we would
right.
have got a hold of him,
So
he might have
he
made it.
wanted a Skype wake up, didn't he?
That's right.
Yeah. Okay. Sleeping
Yeah,
in the
well,
pod. I'm joking.
uh-huh. Well, I guess if we ever get to that point in life, we could do the same too, right?
It's a bit crazy. I don't listen to the media very much, the mainstream media very much, but it's a bit crazy over here with the Brexit. It's like it's someone was saying it's like the 1930s over here.
Is the Brexit
Brexit thing is
about to
kind of like
happen?
someone was saying on the I was watching a little bit of television somewhere else and yesterday and or the day before, and someone was saying making any predictions in British politics is a fool's game at the moment.
Uh-huh. Yeah. Well, I remember they were saying that Britain was going to go down the tube as soon as they, because of that. And from what I hear, everything's going great, if not better.
Sorry, what was that? Everything's
From
going.
what I've heard, everything's over there is going great, if not better than.
Yeah, if you don't listen to the media, you'll be all right.
Yeah. Exactly.
I think the term is more appropriately propaganda, not media.
Yeah, propaganda. That's right.
Yeah. The medium is propaganda. Yeah.
Sorry, Michael.
I said the medium is propaganda.
Yeah.
Yeah. The medium is media. That's the ether of the media. So yeah,
It's big corporations. What do you expect? They're just marketing arms of larger corporations. I don't know how many years back it was NBC was owned by General Electric. It's just their marketing department. How can they get more government dollars out of, that was worth tens of billions of dollars worth. The marketing department of NBC was a pittance. They didn't care if they lost money or made money from that. It didn't matter. They made money off of the government, selling contracts to the government. Anything to optimize that.
And in these, when we had do you remember the recession of 2008? The stock market crash of 2008.
Absolutely. Yeah.
Well, these billionaires, when they lose, they were complaining they lost millions, but that's, to them it's just like £5. £1 million is like £5 to them. Not so much money.
Oh yeah, there were people afterwards in the bailouts. They I think like Goldman Sachs secretary was getting $1 million bonuses or something like that. You know, so they weren't doing too badly.
Anyway, I thought what we could do is have a little look at the ETD stepper.
Great.
Let's have a look here. If I just share the screen. Press share. Stepper. Can you see that?
Not yet. Well, I see it black screen
now.
Oh
Yes.
Yeah. Yeah. So what I was thinking is, I mean, it's a little bit. It's not beyond me totally, but it's a bit above my level. But I'm
okay. So .h files are include files.
Okay.
So what they're doing is they're including all of these things and setting up variables, and calling functions to initialize things. So whenever you got a .h, it's setting things up. So they're reading the configuration. The first thing in that first function, they read the configuration, and that's the function following it.
Right.
And so
that's this one here.
Yeah, if you want to go it step by step, we can go through it.
Okay, let's go. Might be helpful for other people as well. We're looking at this.
Sure.
So this is the header file. So that was well, you just there it is called there. Include
right
model.h. This is the header file. Model.g.h.
So a whole bunch of variables are set, and some functions are called, reading the configuration, initializing coefficients, initializing conditions. So this is where everything's being set up, and doing a normalization.
Okay, so whereabouts in this file, this main file, model g.cpp C++ main file, whereabouts in this can I find the actual say one of the equations, like the dg by dt?
Okay, let's scroll up to the beginning of the function that you're on right there, that void model. So this first function is just basically doing some initialization.
This one here.
Right, so that's just reading configurations, initializing coefficients. So you're initializing things. So the first function that is defined there, we don't necessarily see where it's called, but let's at least look where it's defined. So line 14, 16, 17
line 14,
is
14, 15, 16, 17.
Okay, so here you're reading in the configuration. So you're just getting lines. Okay, so a stream has been passed in. String line, streams. Okay, so configuration. Okay, so config was defined earlier in the configuration. They must have had the stream defined. Okay, so that's probably just the file that they put all of the variables in. So there must be a within the config. So we can come back to that later. But So while SS is not in the file, okay, so it looks like it's reading in A, B, DX, DY, P, Q, G, ST. This looks like it's STOD line substring. So it looks like they're doing a read of string to decimal, S2D, okay? So it looks like they're doing a conversion from a string to a decimal. So it looks like all of these variables are being set, you know, they're reading in the strings and they're converting them to decimals.
Okay, they're converting them to strings to numbers.
Yes. And not integers, but decimal numbers. C cares about that because C is closely managed to how things are stored on from an assembly perspective. Relatively low level language. So then G0, okay, so we've read in those values and now we're doing some computation. So we're getting G0, X0, Y0. So those look like those are actually quantifications for the different types of etherons.
So what would say WB here? W. Do you know that would be?
Well, let's if you can bring up the paper and let's look at an equation for G.
Okay, let me just get the paper. Model G.
Yeah, let me get back. Got to change the temperature here.
By the way, Darren, did you, I mean, Brendan.
Yep.
Did you manage to Skype
Paul?
Paul?
No, I didn't. I don't know his Skype number.
Oh, me neither. How about you, Justin? Do you have Dr. LaViolette's Skype?
No, nope. Closest I've gotten are these meetings. I've been doing mostly email with him.
Well, he wanted a Skype wake-up call last time.
Oh, none of us have it.
Yeah, I had asked for it, but I don't think he replied with it.
Well, send him an email.
Might work.
And in the email, tell him to send us his Skype, or I'm sure he doesn't want to post it in the Facebook.
Okay.
Yeah, and I'm gonna have to leave top of the hour. Just a heads up. I won't be able to stay too long.
Okay, so that's another 40 minutes.
Yeah.
There we go. It should have it somewhere around here.
Okay, so
that one there.
Okay, so let's put that side by side.
Okay.
Because the code only uses about half the screen. And it looks like the paper can use half the screen too.
See that?
Yeah, okay, so the point is not to zoom in, is to have it half the screen the paper, and half the screen the code. So I would shrink it down so the paper's half a screen, and then put that next to the
right. Let's just take that.
The code. So, and you could scooch the code over to the side, so there's room for the paper.
Okay. Just like that. What about that? Can you see that? Can you see that? Okay.
Yeah, sure. That's not a problem. We're just not seeing the code.
Let's just I can scroll that. I'll make this smaller. Is Michael still there or is he gone?
I am.
Okay.
Here's a cat saying hi. Whenever you're on, he keeps walking by.
Here are the Model G equations here.
Okay. So can you put that right next to the code so we can look at it side by side? Can you get, what you can do is you can typically split the browser, so you got two different browsers up. You can split the tabs by browser by just sort of dragging the tab off.
I've dragged the tab off here. Can you see? So
no, I'm only seeing one browser.
what are you seeing? Can you see them both?
I'm seeing the paper.
Only. Okay. So how do I do that then? How do I split them? I've got, I mean, can you see, you can see the paper there.
Yes.
Can you see that one there?
Nope.
You can't see the code.
Nope.
Okay. It's
All
only
right,
showing one screen. It's only showing one screen then.
Right. So you can't put it on two different screens. You have to put it on one screen.
It only takes one screen at a time. Okay, let's just put this back.
So just put them next to each other, one screen, you know, just shrink the browser size down.
Yeah. Okay. What I'll do is I'll okay, what I'll do is I'll just like go from one to the other, just like that. Okay. I'll just go. You just go. Tell me when.
All right. So let's go back to the code.
Okay.
Okay. Let's look at the equation that we had for G.
That's good.
Okay. So we have G0. So we've got A plus GW divided by Q GP. So let's go see if we can find that anywhere in the paper.
Which one's that? This one here.
The G, yeah, the first G.
Divided by Q, G. Okay, good. Let's go to the paper. Okay.
Okay, so we've got
well, it'll be equations 13.
Equation 13. You want me to go to that one?
Yeah, that's probably closer to the mark, I would guess.
so we've got the change, the partial.
Excuse me.
We've got Q and G there.
Q and G. Yeah. Q and G.
Well, not just, excuse me, yeah, Q, G, and all right. So let's go back to the code. Okay, so we've got A plus G, W plus Q. Okay, so this is initial conditions. Let's scroll down this code first because that's just setting things up initially.
Initial conditions again.
Well, you're scrolling too fast.
Okay.
You need to scroll up a bit.
Up a bit?
Yeah, because we don't know where this code is called, this initialization. So scroll up, you know, to 16, 17 again. And
16, 17.
So this is reading the configuration in. So reading the configuration in is doing, okay, so it's doing all of those initialized settings. So then it does the config close initial coefficient. Fine, okay. All right, so the final thing is probably calling model G. So scroll down. Okay, so this is just initialization. So what are, A is like the alpha, what is that? The
Go back to the paper.
yeah, is that the alpha etherons or?
There's initial conditions of the state of the reactions. Those are like reaction variables, like the
Yes.
A, all those different terms, alphabetic terms.
Okay, so here we go. So we got A, okay, so that's the equation 11 that we're doing right there. A plus GW divided by Q minus GP. That's probably the exact equation we're looking at. So let's go back.
What does G0 stand for? Like
initial conditions, where you're starting.
Starting, finishing. Okay.
Yeah, the number of it. And wasn't it A? Okay, so let's go look at the equation. You can see it.
Go to the code now, you mean?
Yeah, because that's 11. Okay, we're looking there. A plus GW, go back to the paper. A plus GW, exactly, divided by Q minus GP. Go back to the code. Q minus GP. That's exactly that equation.
That's like the background potential, essentially.
Yeah, the initial condition, the stabilized version, the kind of stabilized
Right.
background.
And the exact, okay, so let's continue looking at just this function. Okay, so let's go ahead. So there's PA, QW, and it's Q minus GP. So go back, and that's exactly that one. Yeah. Okay. So this is exactly it. So now let's try and look at what those values are, because that's defined somewhere. So let's go look at the. Okay. So we know where equation 11 is. So we've located one of the equations and where it sits. But let's look at the variables and where they came from. So let's go back to the code. Okay. So scroll up, because they're getting all of this. Okay. So they're getting lines. So they're getting a line from config. Scroll down a little. Okay. So this is the read config function. See, model G : read config. So if you see over there, do get line, config line, while line 0 is not equal to. Okay. So it's
Hello, Paul.
Hi. I was working, trying to finish an email and was a little late. Sorry. I won't be able to stay too long because it's 11:30 at night here. So I'll be just for maybe 20 minutes, half hour.
okay.
Justin's just stepping us through the code, so this will be like a tutorial session.
So exploration. I haven't gone to the code to this level before either. So we're getting get line, config, and line in there. So let's go see where the config is coming from. But if you can scroll up. Okay. So we got config file name. So there's some config file name that's being passed into this function.
Whereabouts is that? Config file.
Well, let's go out of this and see if we can find that config file just
in the header file.
It may not be in the header. It may be. It may be. Let's see where it's defined. We can see if we can find the config file. That model G.h. You can check there if you wanted to look at it.
Model G.h. That one. Okay.
Yeah.
David couldn't make the meeting.
He left a message in Facebook that saying he had trouble getting ET Stepper working, but he was working on a let me just get that up. So he's left a message here. He's left a message here. He's just left that message there.
Yeah, I don't believe there's much to report in terms of actual simulations being ran. So this is probably more of a working meeting, right at the moment.
Okay, so Justin, we were looking at the header file, or what? Go back to
Right. Yeah. Let's continue looking at that header file and see what we can get out of it. All right. So we're including another H file. Read config. So it looks like config's already started by the maybe in the ETDR K4B. So those are the variables that are being used throughout the program. Let's just scroll down a little farther, see if we can find anything. So we got file name, model G constructor, file name. So see
Are
if
you just trying to locate where they're being initialized right now? Is that what you're doing?
Yeah, well, not where they're initialized, where they're defined, because the initialization code we're seeing things that are being reading. We're trying to see what those initial values.
Well, that's in the paper in equation 17. If you want to call it equation, it's just a table of values.
Okay, so let's look at equation 17, but we're gonna see where in the code it is.
equation 17.
So we've already identified where in the code one set of equations is. Okay, so here we have some values. So let's go and see if we can find those Well, if you look at this set, dx, dy, a, b, g, let's go ahead and look at the code, the CPP code, and you can see that those are exactly what's being read in there. Okay, so we got dx, dy, a, b, change the order of them, then p, q, g, s, u, t, uw. Okay, so see those match. So this is where they're being read in, but we have to see where the file is, where these specific values are put in. Okay, so let's go back out to to the directory of files that right. So let's go ahead and look at that. I think it was the H file, not this one. Yeah. Right. This is just a definition. Hey, it's probably in some type of, probably not an H file. Let's see what's going on here. Initial, calc K, because they're literally being read in as strings. So let's go out to the directory again and see where we can find. Let's try that text file. Maybe that's
that one there.
Yeah,
that one there. That one there, Justin.
Yeah.
Apology.
There they are.
Yeah.
That's them.
Okay, so let's see if these values match the paper. A14, B29.
Yep. dy is equal to 12. Yep.
Okay, so anything with that hash mark or pound sign, whatever you happen to call it in whichever country you're in, let's go back to those numbers, is a comment. And if you looked at the code, all of those things were being ignored. It was only when it came to
just the line that says system constants is the one that's being commented, not the line below it.
Yeah. Okay. So there's other things being read in. So this is one thing that's read in. So we can go back. We're just going through the code step by step. So we've identified where at least some of the equations. We found line 11. We found line 17 in the code. Okay. So 2 successes.
Yeah.
And we can modify those now.
What about so what's the next one to go to? They're down here?
You know, when I'm looking at code, we can go any directions you want to go. When I like going into the code, okay, we saw all those numbers. I'd like to go personally back to the code to see where all those other numbers are coming in, so we can understand what those other numbers are in that modelg.txt file. So that means that we need to go back to the main CPP code to see.
The 50-50-50, that's the size of the cell that's being.
Okay, so scroll up. So we've got lines 43, 41. We're all the way up to here. We got the if. So we name these lines substring 0 inline find equal. So that's where you're finding things. Okay, is less than line. Okay, so scroll up because there were other numbers that were being read in. So scroll down to like line 20, line 21, line 22, 23. So we're getting a line there while line is equal to pound, it's going to continue to get, okay, the lines. So it's going to ignore everything with the pound in there.
Where's that? Whereabouts is that? Which line is that?
23.
That one there?
Okay. So let's look at that text file. Okay. So let's go back to the text file. Since we're getting some traction on this function, okay, So it looks like it's going through the hash mark. It's ignoring, and I know what's doing with the 200, 256, 1, 50, 50, 256. But then 12, it's paying attention to. So it looks like
resolution. 256 is the resolution of the computation within the cell.
right, but we need to see where that's being set in the code. This is one way of approaching how to figure it out. Another way is to try and find the different equations. But since we have some traction on this piece of code, let's go ahead and try and find it.
Can Matt help out at all to let you know where he has certain things?
Well, he's invited us before. I mean, this is pretty standard stuff. It just takes time. So we've invited him before. He hasn't come, so we might as well go.
I mean, I think he'll agree to help out to answer an email and stuff like that. He just doesn't want to, take part every week. I think.
Right. Okay. Well.
Special, just 10 minutes of his time, something like that.
I mean, it's a question of just getting started, getting into it, and
right?
Getting flowing with it. Once one gets into it.
Right. So I mean, we could provide some equations. Say, hey, we know that these lines line up with this equation. We know that these lines line up with this equation. And sometimes it's several sets of lines. Like it's this set of lines right here lines up with equation 17, but also the lines in the other file, the TXT file, line up with equation 17.
So you're getting a pretty good grip on what Matt was doing.
Well, we're just starting. This is the first approach, and we've narrowed down a couple of equations, and then as we step through it, we're going to understand more and more of the equations and more of the different methods that are being used. But it's going to take time, and everybody's doing. Well, I'm doing it part time. I don't know about Brendan and Michael. I think Michael's doing it part time too. I know Brendan. I know what your time schedule is on this.
I've got time. I was having a look at it every now and again.
Okay.
It's a little bit above my level of programming, but it's not. If I get into it and work through
it.
Okay.
So I think you're starting to get a feel for it. Yeah. So I think going through it line by line will help you understand the code better. Since I've taught coding before, being told where things are helps, but also stepping through it helps. So perhaps after this. Or maybe this in another session, then we can, have enough knowledge to send them a clearer question to Matt. Okay, that might, but I think we should probably go over to pass or two, make more sense of it. So at least we're saying, hey, we understand where some of this stuff is. We're just working on the tough stuff. He might just say, hey, just go through the code because we have some understanding of it.
Once you've got a proper question, good question.
Yeah, I mean, this is just the beginning stuff. It's straightforward. Okay, so let's you make a good point. If Matt's willing to help, we can try and come up with a good question. But let's continue going through it at this point. So Brendan can get a better idea, and everybody else, Mike and myself, because I honestly haven't stepped through it before.
You could run it for say 10 minutes or 20 minutes just to get the first one or two outputs.
Let's try and get those other variables. I think, because Michael has some knowledge of what they represent, so I think it makes sense for us to figure out where they're being pulled in.
These ones, so, we're talking about these ones here?
No, that the 50 and the 256, are they in one of the equations, Michael?
That's the size of the Q that you're analyzing. So that's like the boundary.
Is that set anywhere in the paper, or is it purely in the code?
No, I think that's probably just in the code. Well, but then he does. He only displays the results in the paper after that. You can see it graphically. You can see the charts where you can see it goes from like -20. But no, I think it's just in the code.
Okay, so let's see where these are pulled in the code, because we can see that over here it's looking for anything with an equal in it, and that line is the only thing with an equal in it. So even if it were given the whole file, that's the only thing that would be pulled in by this code segment. It doesn't seem to matter too much on order.
Okay. Okay. So,
Okay.
Just to correct myself, actually in a paragraph just before equations 14, he does set the reaction spatial domain as minus 50 to 50. So
which one here? This here?
Yeah, right.
Yeah, that was just before equations 14 in the paragraph. Or actually, it might be, you can consider part of 14 because he writes that.
Minus 50, 50 R is the reaction spatial domain, and total time is specified. So okay, so time is 100.
Or yeah, you just read that mathematically.
That looks like a radial. What has he got? A radial dimension? Radius in the case of 2D and 3D. Position in 1D and radius in case of
circular symmetry.
Boundary.
That's right. Yeah.
It's a radial
circular symmetry, like Paul said.
Say it again.
A circular symmetry.
Circular symmetry, yeah. So it's one dimension is X, and the other two dimensions are specified by, well, no, that's R. How is that?
Circular symmetry for 1D because the computational demand was a lot lower, so he didn't need to do that.
All right, so I'm not sure how we're getting 3 dimensions out of the.
Is it supposed to be? Is it other dimensions the particles? Instead of 2 dimensions, there's 2 particles. 3 dimensions, there's 3 particles.
No, that's just dimensions. So 1D is just X and Y.
Okay.
Cartesian.
Yeah.
Yeah.
You're gonna have to read over the paper. Okay, so
yeah.
If somebody can answer that question, how we're getting,
Yes, because if you have
I just want to tell you that I'm here now. David from Sweden is here.
Okay, hey, David, how you doing?
Hello. You can continue.
If you look at this one here, duplicate, go up here and have a look at the Mathematica program. Subquantum Kinetics.
All right, you're going fast for me.
So this is the Mathematica program. I noticed that he placed.
Run this one.
I noticed. Can you see cylindrical coordinates?
Okay, yeah.
Cylindrical, spherical.
Spherical, okay.
Cartesian, X, Y, Z.
X, theta, Z. Okay, so that I get. But we've got a radius and an X position. So I'm not sure how we're getting a coordinate system out of those two.
Maybe Matt can answer that.
Yeah, that would be a good question. But let's continue going through the code. I think it typically you try and go through code and answer as much as you can, and then with the file, throw 2 or 3 questions each time. All right, so let's continue going. So we identified that for David's edification, lines 41 through 43 match up with equation 11.
11 in here. Match up with equation 11.
Okay.
No, not 11. Yeah, that was that one.
Okay. And then the other lines above that, lines 39 through 39. Perhaps all the way up to 21 or something like that. But particularly because they match up to 23. They match up with equation 17.
Equation
17. But there's a second half of that.
Equation
because
17.
there's a TXT file that's associated with it also. So if we go to the TXT file for equation 17, we can see all of those. So all of that code was to read through this file, find anything without a hash mark in front of it, and also with an equal sign, and then use those equations to set up variables.
Oh, by the way, while you're looking at that, if I remember correctly, and you can verify this with Matt, but just if you want to change the dimensions of the simulation, I think all you have to do is omit. Like if you want 1 dimension, you could just put 150 there. And then if you want 2D, then you have 250s. And then for 3D, you put 5 350s or whatever values you want in there. But that's how.
Okay, that makes sense.
How you change dimensions.
On what's described there. So
Yeah.
so let's okay. So there's 1, 2, 3, 4, 5. All right. So the code we saw before only went through this file and only cared about if it saw an equal. But something's reading in the 200, the 256, the 150s, and the 256, all of those. So let's see if we can find where in the code those are read in. It's probably somewhere in this configuration. You might be reading
that one
the file
is
in a second time.
mod g.text.
Right.
Okay, so what about this one, like a config file name or something?
Well, the config file name is probably that's being set somewhere to be model g.txt. We haven't found where that's being set yet, but it's somewhere. I mean, because we're seeing that that's the file name that actually has that in it.
Well, this one.
Right.
That one.
No, that's being config file name is being used as an as a parameter into it. Active ingredients. Okay. So let you know, as we get through each piece, we'll get a better understanding. Config close. So config is the file. Config file name is the file name. So we're going to read config. So we got string line name, strings ss init I. All right, I'm not sure where we're gonna. So let's
have a look. Shall we have a quick look at this one and see what this is?
Let's go to that model g.h.
Model g.h. Okay.
Yeah.
Model g.h. There we go.
All right. So let's. So it doesn't include of etdrk4bh, which you were suggesting going. So this defines the variables that we're assigning. So in C, you can't just write a variable name and use it. You have to define it first. So this is where they're defined. So that's this is again part of equation 17. So then we do the read config and it decoefficients, set initial conditions.
Okay.
Okay, so let's go where you were saying before.
To this one here.
Because this is we're done with this program, right? Yeah, that one.
Well, if you're in the exponential time diff or exp time diff dot h, it defines like time differentials and things like that.
Oh, wow.
Finet. Okay, so where's Finet?
And that was one of the inputs, I believe, on the text file was time, wasn't it? Time range.
Yeah, he might be reading because it looks like, I mean, from the first read, it looked like that was just one piece of code reading that file, but he might read that in here too. And the reason why he would read the same file in two places is because this is possibly a one segment of code that he got from one place, another segment code he got from another, he built them off different things. They might even read them out. So let's see if we can, because I'm not seeing I'm not seeing any reads in here.
I think it's in the exp time diff.h. I would go to maybe something like line 20 or 30, and I think,
Okay.
Yeah.
Let's go. There we go.
Yeah. Yeah, I've got all the code printed out on paper, so it's easy for me to thumb through it.
Okay.
Yeah.
Oh, so so all those include files are standard libraries that C provides. Oh, well, the FFT, that's a fast Fourier transform library. So there's nothing important in these things. Those are defined. It's just built into the programming language.
Yeah, try maybe like line 40 or 50.
Yeah. So let's scroll down. None of these are really important. Those are all just standard systems.
30.
There you go. See, like line 36. Yeah.
Okay, so all of these are just defining things. So when you define stuff, you're basically grabbing computer memory. And so that's what's happening here. They're just grabbing memory for all of these things. They're not reading anything in at this point.
But they look like they're local variables, so you'd expect them to be used in this file, right?
Yeah, slow down. Okay, so continue on to the vector real. Okay, so now we got vectors defining. Okay. Static Boolean save. Config file name. Okay, so it's pulling in config file name.
Big file name.
Read config.
Whereabouts is that?
Okay, but this read config may be a different read config. Let's scroll down.
Is that one?
Because this read config may be for this program as opposed to the other program. Again, center constant. See, these are all definitions, so let's just scroll through because we're getting the first view is static stability. T sum is equal to 1 for real. Okay, so we're doing something here. Phi with instability. So we're doing a loop and we're summing stuff. This is an H file. We're doing sums here in an H file, in a defined file. Okay, so I'm not sure if, okay, so let's scroll down because this is just, there's no reading being done here. We have to find that read config.
Are those variables case sensitive or not? Do you know?
Yeah, usually in C.
Okay.
If I recall correctly. Let's, okay, so there was a read config. Let's scroll through this a little more so we get a better understanding of all the different initialization functions, dump state, import state.
We've had a little look at that one.
Yeah, that's a summarization, and you know, typically you're not doing that type of code initialization, but that might be some error checking on the initialization.
This is going to be a very good video to rewatch, Justin.
Okay, I'm not sure. It's kind of boring because I don't know. Let's scroll down. Dump state, import state. Scroll down.
Dump state.
So we've got, okay, G value, X value, Y value. Okay, so we're probably going to want to go to that X time diff .cpp might have the read config in it. I'm not seeing, we still got a little more stuff down here. So right float, right calc K. Scroll down.
I'll be leaving the meeting. Sorry,
Yeah.
Late here.
Yeah, it's probably boring to you if we're stepping through code.
Oh, it's interesting, very interesting. It
Okay.
looks like you're making a lot of progress.
Well, we're getting familiar with the code step by step. I mean, usually it takes a few hours. It's time, and you know, if we could put 4 or 5 hours into it, we probably understand the code pretty much and have a good set of questions, if any, for Matt. See, there's other things. There's algorithms associated with it because stepping through the code is one thing and matching up with the equations in your paper is another thing. But then there's the Runge-Kutta method, and you know, I haven't done that in years, and that takes a few hours to go through. And I think there was another method that he used here, so that takes a few hours to go through. So each one, it just takes time. Okay, yeah. So reaction, yeah. So scroll down. Let's see if there's anything else here. I'm surprised the read config is not in this one. Let's
see you then. Okay. See you next week.
Okay.
Bye, Paul. Nice seeing you.
All right.
Have a good one.
Okay.
Okay, so let's scroll up and see that call to read config.
Call to.
No, there's a call a little further down, like line 25 or 30 or something like that.
Call to reconfigure.
No, scroll down. It was in here, I think. It might have been the other file.
Well, which file? The one
So can you search for read on this file on this page name? Read config.
Read, search for read.
Yeah, search for read on this line. Try it again.
Read.
There we go. Okay, so it is in here. So scroll up. Where's it getting that specific read config from?
Read config. Okay, let's have a look at it. Read config.
Not defined here, so it's kind of being one of the other files that we had. So,
or it could be one part of the library, right?
no.
That defined above, no?
No. Most of those libraries are just standard stuff. This is specific to this code. So let's look over it at the XP time diff. What file names we got there? Let's look at the directory.
We had it up here before.
Yeah, you were just 2 over to the left from where you are. You just clicked on it.
That's the. You want the CPP?
No, it may be in there, but let's see what the other options are for the EXP time diff. If there's anything else there, 2 over, 1 over from there, 1 over from there, 1 over from 1 further over. No, the other way. Yeah, there you go. There you go. So where we have the xpine diff H, scroll up. So you're right. That's the only thing we got. Let's see if there's a read config in there. I mean, we're going to miss things as we're making the first pass through.
How long this is? This is quite big.
That's the biggest file probably.
Right. Let's see if there's a read config in here. You do a search on this. See if we got.
What I just do search on
read config.
I'll put read. There it is there.
Oh, there it is right there. Config. It's just a call. Where's it? It's fine.
Can you actually search GitHub? Do they let you do that?
What's that?
Can you actually search GitHub for
Control F and.
Well, no, yeah. What do you mean?
For like all the files, I mean, searching the whole.
Yeah, okay, do you want to try that? Okay.
Yeah, go up to the GitHub page, which is 1 to the left of the page we're on now.
This one here.
Yeah.
This one.
Did they give you the option to search all the files?
I'm not sure how to do that. I wouldn't know. I'm not sure how to do that to search within.
I think I've seen it before. Scroll up. Find file.
Find file.
Do a click on find.
Maybe.
Find file there.
Yeah, just see what it says on find file.
Search. Search here.
No, it's not going to give you anything.
There.
All right, I think we're okay. So this isn't giving us much results. So let's go look for some equations.
Okay.
So what are the other important equations in here? Because I know a lot of the equations are intermediary equations.
This is a C. This is induced momentary seed fluctuation. So that's just a function to initialize, I should imagine. I've got 5 hours for this. If you want to go on longer, I put 5 hours on the each week on the Zoom conference.
Yeah, I think I would. Okay, so I would need to read the paper again to get a picture of what everything is.
Let me just see what he's saying here about dimensions. They're talking about 3D particle formation. So what is this? Is this, what I was thinking is this x-axis, this could be a slice through 1, 2, or 3 dimensions. And on the y-axis, we've got the concentration in 1, 2, or 3 dimensions. The x-axis is just one-dimensional space.
Oh, so he's just doing the radial from that distance out. Oh, that's why it's just radial. He's not finding any specific location. He's just doing radial. The distance away.
Say that again, Justin.
Yeah.
He's just doing.
Justin got it. Yeah.
So okay, so he's not even doing quantity at a specific location in space. He's doing quantity at a distance from the center.
So this y-axis would represent 1, 2, or 3 dimensions of concentration. Is that right?
Yeah. So all the sums are coming together. Okay, so that makes sense from a radial perspective. Okay, so he's not working with specific positions like the Mathematica had. Here it's, okay, here, let's find a position in space
These
and then look
graphs,
at the concentrations and the radius
Justin,
around.
these graphs come from Mathematica. If you run the Mathematica program, you get graphs like this.
Yeah, but I'm not, potentials, okay, those are just potentials, yeah. Quantities, okay. But it makes sense now, the X and the R. Okay, so it's like a quantity, because you can talk about quantities of geons and exons and yons a distance away from a specific point. And that's what the radius would be, the distance away. I'm not sure how you're going to get negative and positive.
Positive, what
No,
negative
there
and
is no
positive?
negative for
Above and
radius.
below the stationary value. This would be this would be like G0, GXY0.
He's doing those in 1D along.
All right, I have to get to the. I have to read the paper again. So we really don't know what the X and the R is. I hate providing questions if I haven't done enough research. If I haven't done enough due diligence, or at least some due diligence. Oh, there's an R. Okay, so I think I need, before I'm sending any questions, I'm going to read the paper if I have time this week and look at the code a little more. Maybe we can come back.
That's a good thing. That's what I'm going to do as well. Just read the paper and try and identify. You've given us enough clues through stepping through the ETD stepper. So now we have to just match up the paper to the ED stepper. Okay,
so the model G is easier because, hey, those are the equations that we have here. The other two are methods and have algorithms associated with them. So you have to understand those algorithms. You have to go to look at a paper to understand what the algorithms are. And he might actually have the specific papers that we're looking for. If somebody could identify, he used the method, the Runja-Kutta, maybe we can scroll down to his bibliography and see which papers, because he may be able to send us copies of the papers, or maybe not, or maybe we can get a hold of some of the papers for let's say the Runja-Kutta method he used, and there was also another method that he used. Runja-Kutta is just, I think, partial differential equations, and I think there's another thing that he used there.
That's all the
localized patterns and reaction diffusion systems. That might be, I don't know which of the papers. We have to go read through it and figure out which of the papers we need to understand.
Well, he came up with that on his own.
No, he used standard methods. I remember reading the paper. He used some methods out there. He found some papers. I think he used a standard method in one case. In another case, he found a specific paper on a methodology to use, and then he wrote code based on that for this specific case. So yeah, he did come up with his own stuff, but it was based upon
What are we going to the paper where he references that as a
yeah, that'd be great. So we're pulling this apart in different ways. Okay. Ginsburg, Landau.
I didn't mean to talk over, but I mean, I went to the same university as he did, and they teach all that stuff pretty standard.
Yeah. Runja-Kutta is like, that's, sophomore.
Yeah. What's that Runja-Kutta? The one you're talking about? That's
that's sophomore junior stuff.
It's a numerical solution technique.
It's standard stuff.
Okay, let's have a look.
So there was some code that had that, and so that was the standard. Yeah, I think that was it.
This one here?
Yeah, you got the ETDRK. So RK is probably Runjakuta.
That one there. That's the header.
Okay, so let's look at the Runjakuta and see what it's. He has comments at the top
That's
of it, I believe.
header. Again. Okay, let's go back to that one. Okay, this one here. This one here.
Yeah, it might be in the H file, might be in the CPP file.
Okay, this is the CCP file.
Right.
Just pronounce what this.
Yeah, so it's a 4-stage Runjakuta, but it's an exponent time difference.
That's the one.
4-stage Runjakuta method. So you first have to follow up with the Runjakuta, understand what it is. I haven't done it in decades, so I'd have to look at that, and anybody can. And then the exponent time difference, that might be the paper that we may want to get a hold of, because I don't think that's necessarily a standard thing, the exponent time difference, exponential time difference part of it.
Yeah, I'm not too familiar with that.
Okay, here we go.
Okay.
That's it. That's the C plus.
Yeah, so Runjakuta is more of a methodology for keeping, for preventing errors, for closing. I think typical numerical methods work on that, but they also have methods for, solving for differential equations, partial differential equations, etc. Exponential time difference, that's what it looks like to me. There might be a paper, so there's something describing this algorithm. You got the Runjakuta part of it, but you have also the ETD part. And I'm not sure, it's a 4-stage, so 4-stage. So the RK4 is for Runjakuta 4-stage, so you have to look up Runjakuta for 4-stage, and then there might be a specific paper on the exponential time difference. So let's look at the bibliography and see if there's anything talking about the exponential time difference.
Exponential time difference.
You can, I don't know if you can search through the paper or not. I think PDF.
Search. What do I want me to search?
Let's look.
Runjakuta.
No, you could, but let's look at the bibliography and see if there's anything with that title in it, just as a start. Or you could look both in the paper and in the bibliography. It depends on your searching tool.
Let me just
yeah.
Okay, let me just put this in.
He may not have that. He may, in this paper, that might be too low level for him to talk about in the paper.
Yeah, he may not mention. He may have just.
But the exponential time difference is something that he likely did. That's more, I think, the level of a journal article.
Exponential.
That's not spelled right.
Expo
N-E. I think you got the E and N mixed.
Okay, let's try that.
But any math you use, it should be here in the code, unless it's a library function.
Often when you're writing papers, you don't put all your working in. You just put the most important part.
Right. The time difference, you might put the word time in there. Let's look at the bibliography and see what we got, so we get a better idea of the different things, algorithms he was using.
Let's go to the top. So interactive dissipation solutions, particle-like structures. Reversal properties of.
I just scroll down, so not too fast, but Okay, so we can scroll through the Laviolette's articles. They're not going to be talking about a mathematical method definition, usage maybe, but okay. So we got lever dissipative structures in chemical systems, rotating bound state of dissipative solitons, spiral solitons. So scattering traveling spots. Interaction of self-organized quasi-particles in two-dimensional reactions. Chemical. Scroll down past Turing. Is that Alan Turing? Wow. Localized patterns in reaction diffusion systems. Rotating chemical reactions. Yeah, I'm not seeing any methods in concentrating wave pattern.
What about going back to, let's just go back to, where is it? Let's go down.
Yeah, EXP time diff.
He's given a reference here, obviously. 4-stage. That's his reference, I suppose, in the code.
Yeah, okay, that's good enough for that part, but also the exponential time.
That's a class that he created in EXP time diff.
That's an algorithm of some type, the exponential time diff.
Yeah, but it's a function that in the code. And that
okay, so he's got
that's defined in EXP time diff.h.
So we've got the Runge-Kutta 4-stage, and we can probably do a search of Runge-Kutta 4-stage, but then we have to understand what the ETD part is, which.
Well, that's what I'm saying is if you go to the EXP time diff, you can read through the code, and that's where it's being done.
Right, but there's also some theory behind it, and that helps too. So when you're pulling a code apart, you look at the algorithm that's being used. So 4th order Runge-Kutta 4-stage, 2nd order. This is 4-stage. 4-stage is more not the order of the algorithm, but 2 stages. 2 stages. Okay, stages are usually how many steps you're doing it in. You do stage 1, stage 2, stage 3, stage 4. So it's like 4 loops or that type of thing.
Yeah, I would guess iteration, but I don't know for sure.
Yeah, that wouldn't be, doing 3rd or 4th order equations. That's, it's probably doing, I don't know, maybe a couple orders and 4 stages to handle. I'm not sure. Well, what's the order of the equation?
RK4 method.
That one there.
Oh, scroll down. We just saw RK4 down there. Yeah, okay.
Okay, whereabouts is it?
All over here.
There.
4th order method, meaning that local truncation error is on the order of, okay. So here we found out what our RK4 is. So we found some definition of it. So we can dive into that.
Okay, so it's a more precise equation.
Yeah. And then, now you have to find some description of the.
Okay. Well,
so this is high level.
Everybody, I have to get going, but.
Hey, Mike, it's been great. You have an excellent week.
Okay, Mike. Thanks for your contribution.
Yeah, you're welcome. See you next week.
Okay.
All right.
Bye.
Bye-bye.
Bye. Bye.
Bye, David.
Okay.
Bye.
Bye then.
So yeah, if any of you guys have insight, let us know on pulling this code apart or paper. I haven't put the time into it, so I'm
this is going to be a very good tutorial. I will look through when going through the code. I can look through this tutorial to get ideas.
Right. So we got the 4K, the RK4. I'm not sure what the BMAT means. It may just mean his second attempt at writing the code. Don't know.
Which one's that, Justin? The
okay, so you see he has ETD RK4B to represent this. I'm not sure what the B means. I don't think it means anything. It might just be his second attempt at trying to write the code. Don't know. And the ETD is exponential time difference. So you have to look at the Runge-Kutta. I forget. I haven't done it in a while. And have to look up the exponential time difference, what that is.
Is he defining the Runge-Kutta code here? Is he defining it here? He's just taking a method. Is he defining it in here?
No, he's using it for a specific purpose in a specific environment. So it's not just a Runge-Kutta method standing on its own.
With this exponential time.
And so if you're talking about exponential time, that means that time is not linear. So in order to get things that happen over a very long period of time, he's probably using some type of exponential function in order to get things to happen that would usually take a long period of time. I mean, knowing what, the problem that we're applying this to. So that's my guess of that there's some exponential time feature in these, was it fourth order? It looked like was partial differential equations that we're solving for, I think was what we're doing. I know we're doing partial differential equations. I think it's 4 or 5 of them, so. Okay.
What's this here? Is he defining this Runge-Kutta method here?
Find it.
Void, because it goes down. I mean, this is.
Odds are it's both of them together. It's exponential time difference with Runge-Kutta because it's got the ETD Runge-Kutta. So it's like. So I don't think it's straight Runge-Kutta. I think it's, adding an exponential time difference feature in. And Hermitian map, you have to look that up too. I mean,
Hermitian math, whereabouts is that?
line 25.
Hermitian map. So these functions that he's kind of.
The Hermitian is a mathematical term, and I forget what it is.
See.
I'm not sure you're going to find anything under map, but Hermitian you should be able to. That might be some type of coordinate system or what have you. I forget. It is a mathematical term. Hermitian matrix, you just saw it.
I think they studied this in quantum mechanics, I seem to remember. Hermitian, I think. Yeah, they studied this in quantum mechanics. It's just
a mathematical technique that can be applied in different places.
Nothing to do with matrices. It is to do with matrices.
Okay, so it's okay. So a lot of differential equations and other types of complex equation solving can be simulated very effectively using matrix mathematics.
Yeah.
So it looks like they're using some matrix mathematics to do to help solve this problem, and that's usually in numerical methods too. So it looks like they're using some type of linear matrix. Linear matrices to solve these equations. Okay, that can speed up the solution. Neural networks, they do the same thing. It's just linear matrix, linear algebra.
Okay, this is another one. This is
Okay, so we're in the class of ETDRK. So these are all the functions in that class. So that class is sort of a grouping of stuff. But we already have sort of a grouping from the file names. But this in the C code, it keeps them separate so that the file names don't overwrite each other. The variable names don't overwrite each other. So R appearing here is going to be an R different from an R appearing in the Model G program. Okay, so you can use the same variable names, but they don't mean the same things. Okay, so right now what we're doing is we're just looking at stuff and answering some questions, getting a high level view. We're not nailing down any specific equations here. We're just sort of getting a bigger picture. So this is the ETDRK4 stuff. And then you have the exponential time code, if you wanted to go back to that.
This one?
Yeah, because that, not only is it mentioned in the ETDRK stuff, it's mentioned here separately too. So is it,
some of these things,
yeah, you have a couple of them. So I already gave you my guess. as of today. Oh, it looks like we had some coordinates there. Did you see cylindrical in one of those?
Yeah, this
things?
one here. This is the Mathematica program.
Oh,
I mean,
yeah.
it's not,
Okay.
you see, that's the whole program is just like
Yeah, that's.
program is
Yeah, I mean, okay,
not that
cylindrical
large.
systems. That makes sense. I'm still trying to figure out how we get the R and the X that we saw earlier, but
He talks
so yeah,
cylindrical.
this is just taking time to go through this. All of that makes sense. Spherical, cylindrical, those are all standard mathematical coordinate systems. So there's nothing surprising there. Not that I necessarily recall the specifics behind, the spherical and the cylindrical. What's the difference between the two? But they're just I know they're different. If I recall, I know they're different.
If dimension equals 1, if dimension equals 2, dimension equals 3.
I believe with both of them you can define 3 dimensions with all 3 of those. The x theta phi, x theta z, and the x y z. All of those are 3-dimensional.
So the dimension 1 may not mean 1 dimension. It may mean choice 1.
He may be okay. So it may be he's applying the equations to a 1-dimensional system, and then the map that's coming out, he's creating via Cartesian and cylindrical and spherical. But all 3 of those systems are 3-dimensional systems.
Yeah.
Different ways of specifying 3 dimensions. But he's also plotting stuff, and when you plot stuff, you can plot stuff against time. You can
This program only takes about 20 minutes to run, the whole program. I ran it a couple of months ago. Also a year or 2 ago.
Well, I was running the code some years ago, and it took 11 hours to run one step.
This one,
the 3-dimensional solution.
All right, the 3-dimensional. Yeah. I must have been doing just the 1 dimension then.
Okay, all right. Yeah, so we don't need to go through this code necessarily because the correlation between this and the other code is not 1 for 1. I don't think it's going to give us too much help to understanding the C++ code. I really don't think looking at a code is going to help any.
We're not really. No one's got Mathematica at the moment.
Well, it also doesn't provide for running more efficient code. It's going to solve the equations how it wants to solve them. In the code here, you can do Runge method. You can control things at a more fine level, how you're stepping through stuff. You can create, different coding features.
Can I just ask, David, when you're running this C++ code, can you just run it for like 10 or 20 minutes to get one output? Or do you have to run it for the whole 2 days? Can you just run it for like 10 or 20 minutes, get one output, look at that, just to see if it's running?
Yes, it is running. As I wrote today, I had some problems. I was trying to run it in February, and it went some hours, and then I got a deep crash in the computer. I didn't know what it was. So today I analyzed and found that the memories are bad. So I lowered the memory speeds, and I ran the test software, and everything worked okay. So today I started a new simulation, and just to see if it can finish. So if it works, it will be finished by tomorrow.
Yep. So what I'm saying is that if I just want to run it and I'll test something out just to see if it's running, I can run it for like 10 or 20 minutes. It'll produce one output.
Yeah, if you just want to have one frame, yeah, sure you can.
That's the Mathematica or this code?
No, that's C++. That's this code here. If you run it for like 10 or 20 minutes, it will produce one file output.
Okay.
Yeah.
But,
all right. Sounds good. So I'm feeling much more comfortable, having touched the code now. I consider this touching if we can correlate different things in the paper to the different parts of the code. So I feel much more comfortable after today. And maybe that'll get us all into this a little bit more and looking at more pieces. So.
Okay, John, do you want to wind this up now?
Sounds good.
Yeah. Okay.
Okay.
Okay, guys. We'll we'll meet up next week then. See what progress we've made.
Slow progress, but that's fine. I'm doing this part-time at this point, so this is not my only slice at using the subquantum kinetics. I'm also trying to experiment with some materials that have similar properties. So
okay.
all right. Okay.
Yes, I have investigated it there. Yeah, I can take it next meeting though.
Okay.
Yeah.
I look forward to seeing David next week.
Okay. Cheers.
And I look hearing about your results from next week too, David. Okay.
Okay. Yes.
Great.
Okay, guys. Cheers then.
Yeah.
Cheerio.
See you. Bye.
Bye then.